All right, so the next topic we're going to cover is called Electron Configurations. So we know that in the atom, we know that there are electrons that are in different energy levels, right? So this is a Bohr diagram, and remember the Bohr diagram shows different rings or different orbits. And the thing about the electrons is that while they are in these different energy levels, they may be organized differently within each level. So we're going to talk about how electrons are arranged, how they are organized. So a couple rules. So the first rule about the Bohr diagram is that in your first energy level, the first energy level can hold 2 electrons. Okay, so just 2 electrons. The second energy level can hold 8. The third actually holds more than 8, but then the organization gets a little complicated. So we'll start small. So for hydrogen, this is a Bohr diagram for hydrogen. I can tell that because there's 1 proton, 1 electron. For oxygen, which has 8 protons and 8 electrons, the diagram would look like this. Here's your nucleus. This right here would be energy level 1. See the 2 electrons in it? And outside of that would be energy level 2. Now, in energy level 1, there's 2 electrons. In energy level 2, there's 6 electrons, because we just said the total was 8 electrons total, and the second level can hold up to 8, but in this case, there's only 6 to put in there. So if there's 6, then there's just 6. The total is 8. Okay. So let's try applying this to another element like aluminum. So aluminum has 13 protons, 14 neutrons, 13 electrons. So if I were to draw aluminum in the nucleus, I'm going to zoom in here. 13 protons. There's 14 neutrons. So in the first energy level, there can be 2 electrons. In the second energy level, there can be 8 electrons. So because we were dealing with 13 protons so far, and 13 electrons, so far we're counting 10 electrons, which means in third energy level, well, there's only 3 electrons remaining. So this is what the Bohr diagram would look like for aluminum. So the Bohr diagram is great for showing the different levels. But where the Bohr diagram doesn't really hold up is when we start to pick apart those levels and see what the pieces actually look like individually. So the Bohr diagram, it was really the first attempt, right, to show the energy level of the electrons, but it was a little inaccurate. It was a little incorrect. So it turns out that in the atom, each energy level is broken up into different kinds of spaces. So there are levels, 1, 2, 3, 4, etc. But then there are what we call sub-levels. And there's different types of sub-levels. There's S, P, D, and F. And depending on which level you're in, the number of sub-levels will increase or decrease. So let's start from the very beginning. So in energy level 1. In energy level 1, there is one sub-level. It is called S. And so S sub-levels look like spheres. Right? So it's just simply a spherical shape. And it can hold 2 electrons. All right. And that's the only sublevel there is in energy level 1. In energy level 2, you have 2 sublevels. You have the S, and you also have what's called a P. Okay, so you already know what S looks like. A P sublevel looks like a dumbbell. And on an XYZ coordinate plane, there's a dumbbell along the y-axis, a dumbbell along the x-axis, and then there's a z-axis, which is what comes out towards you and into the screen. XYZ. So the P sublevel is broken up into 3 parts. 3 dumbbells. Each dumbbell holds 2, which means 6 electrons total in a P sublevel. Okay, so do you see how like the one sublevel is actually broken into different parts? So that's the second energy level. The total number of electrons that can be held in the second energy level is 8. 2 from the S, 6 from the P. In the third energy level, there is the S, there's a P, and there's a new one called D. So the D sub, notice as every time we go down a new sublevel, there is a new additional sublevel. So we've got D sublevels, which is kind of hard to draw, but just suffice to say that there's 5 parts. Each holds 2, and that makes for a total of 10 electrons total. Okay, oh, by the way, these parts, there's a name for them. We call them orbitals. So when I say 5 parts, 5 orbitals, right? Each orbital holds 2. Since there's 5 of them, that makes for 10 total. Okay, so hopefully you're starting to see a pattern. In energy level 4, there's the S, there's the P, there's the D, and then there's the F. The F sublevel contains 7 parts or 7 orbitals, right? And that makes for, that makes for 14 electrons total, because 7 orbitals, each holding 2 electrons, is 17. Every orbital can only hold 2 electrons. Okay, so this chart goes on. Energy level 5. Well, if it's the 5th energy level, there are potentially 5 sublevels. In energy level 6, there are potentially 6, and so on. So the structure within the atom, where the spaces where the electrons are, with each new energy level, they get bigger, and if they get bigger, they get more complex. So here are the pictures of the S. A simple S orbital is a sphere right in the center. A P sublevel, here is your X orbital, here is your Y orbital, and here is your Z orbital. Here is your Ds. Now there's 5 D orbitals. Each one of these spaces can hold 2 electrons. And here are your Fs, which look even weirder. So the bigger And the more orbitals there are, then the more fragmented they become, the weirder they look. So you don't really need to know what these guys look like here or here. I would say that you need to know what an S and what a P sublevel looks like, but beyond that, we're not concerned with these weird shapes, with the Ds or Fs, so you don't have to worry too much about those. The main thing that you need to know is how many electrons can be held in each sublevel. So again, S's hold 2, P's hold 6, D's hold 10, F's hold 14. Okay, so to answer the question, if this is the number of electrons, the number of orbitals, since there's 2 electrons held in S, that means it's only 1 orbital. Since there's 6 electrons held in P, that means there's 3. For D, there's 5, and for F, there's 7. Okay, so now we've broken down the different energy levels and the types of spaces within. We need to actually apply this and see how this works out with our understanding of the atoms in the periodic table. So on a typical periodic table, which is arranged, we read it like a typewriter from left to right. So right here where my cursor dot is, that's hydrogen, that's atomic number 1. Helium is over here, atomic number 2. And after that comes atomic number 3, which is here, then 4, then 5, 6, 7, 8, 9, 10. So just like a typewriter, okay, from left to right, once you get to the right end, it starts over. And then you begin again. So from left to right, left to right. So the first 2 columns on the periodic table, this is what's known as the S block. The 6 columns on the far right side is known as the P block. And then there's kind of a valley here with 10 columns that's a little bit lower. This is known as the D block. And the F block have been removed. They've been kind of pulled out of the periodic table. Normally the F block goes in right here. Right? This gets inserted there, but it's, for the sake of fitting this on a piece of paper, they take it out. That's the F block. There's 14 columns. So hopefully you're noticing that the number of columns in each of these blocks represents the electron capacity of that sublevel. Okay. So going back to the diagram that I had shown you at the beginning, this is called the order of fill diagram. And the way it works is you read the sublevels in the order which the arrow hits them. So the first arrow that comes down, the first arrow here, right here at the top, hits 1s. Okay, and then once we get to the 1s, we start the new arrow. And this arrow comes down, and this touches the 2s. After the 2s, we start a new arrow, come down, and now we hit the 2p. And after the 2p comes the 3s. The new arrow comes down and hits 3p. And then it hits 4s. And the next arrow comes down, and now the next arrow hits 3d, which is odd, because normally you'd be thinking, oh, well, what comes after 3p? You would think that 3d comes after 3p, but it doesn't. 4s and then 3d. So the order starts getting kind of wacky. After 3d comes 4p, then comes 5s, but after 5s comes 4d, and then 5p. So the order gets really weird and almost unpredictable. So that's why we have this diagram. This order fill diagram it's not something you'll have to remember, and you'll be given it, but we use it to determine the order in which the subshells fill. Okay, and so what that means is if I picked an element, like here we're showing sulfur. Sulfur has 16 electrons. And we want to organize the electrons. We want to write them in the order in which they fill. Okay, so there's a rule that says the lowest electrons fill first. Okay, this is called the Aufbau Principle. Aufbau is a German word. It means to build up. All right, so since I counted 16 electrons, 1s fills first. And that's because it is the lowest energy level number, right? It's the one closest to the nucleus, and that fills first. This is the Aufbau principle. And since there's 16 electrons, and since I know each s sublevel holds 2, I write the 1s, and I put a 2. After that comes the next sublevel, which is 2s. So we write 2s, and s's only hold 2, so and they get full once they're at 2, so we write a 2. After 2s comes 2p. Now p's hold more electrons. They hold 6. So we write 2p and we write a 6, and that brings us here. Now so far in this block here, this is 10 electrons so far. 2, 2, and 6 is 10. After 2p comes 3s, and s again holds 2, so we put a 2 there, and that's a total of 12 electrons. After 3s comes 3p, and p's can hold 6, but we only had 16 electrons, right? And so if we went from 2, 4, 10, 12, that means there's only 4 left. And so we just write the 3p and we write the 4 because that's using up all of the electrons. This is what's known as Spdf notation, because it's notation using the sublevels SPDF. And it's a way of showing the electrons, how they're organized in whichever element you're referring to. Okay, so there was a bunch of rules, and there was a lot of things going on here. So the best way to learn how to do this is through lots of examples. Okay, so let's do a couple together. Nitrogen. Nitrogen has 7 electrons. Aufbau principle states that you always start with the lowest, and the lowest is right here, lowest. Even though it's at the top of the diagram, energy-wise, it's the lowest. All right, lowest means closest to the nucleus. Okay, so 1s, and s's hold 2. What comes next? Follow the diagram. 2s, s's hold 2. After that, we start a new arrow. The next sublevel is 2p. So how many electrons do you think we fill or we write above the p? Okay, so if you said 3, then you are right, because we only have a total of 7 electrons. And so you only write this as far as how many electrons you have. So this is done. Okay. Let's try another element, chlorine. Chlorine has 17 electrons. So 1s, and we put a 2. After 1s comes 2s. We put a 2. And then 2p. P's hold 6. So right there, if I add my superscripts on those sublevels, I have 2 plus 2 plus 6. That's 10 so far. I've got 7 more to go. After 2p comes 3s, which holds 2. Okay, that's 12 so far. I have 5 more to go. The next sublevel is 3p, and p's hold 5. And that's a total of 17 electrons, and now I am done. I've accounted for all of the electrons. I have written the sublevels in the correct fill order, and I have the correct capacities on each of these sublevels. So these are the kind of things you have to be aware of as you're writing these down for whatever element you're asked to do that for. Looks like we got a couple more here. Scandium. So scandium has 21 electrons. So go ahead and pause the video here and see if you can write scandium correctly. All right, so I'm going to go ahead and write this now. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. And that's a total of 21. We followed the correct fill order. All of the sublevels have the correct capacities shown, except for the last one, because the last one, you never really fill the last one, or sometimes you do, but the last one can be unfilled. That's okay. All right, pause it again and try argon. All right, so I'm going to go ahead with argon. Argon has 18 electrons. 1s2, 2s2, 2p6, 3s2, 3p6. So that's 2, 4, 10, 12, 18. And we're done. So that is how we write SPDF notation. Okay, so this diagram is a different way of showing fill order. It gives you the same information, but it also gives you a little bit more. So in this diagram, you start from the bottom, because the bottom here, 1s is the lowest energy. And so if I just move from bottom to top, then the sublevels that I hit are the next ones that fill. So this is also a fill order. And it will be the same fill order as the other diagram. It's just a different way of showing it. The reason why it's different is because it shows circles that represent the number of orbitals. So 1s, 2s. After 2s comes 2p. After 2p comes 3s. And then 3p. And then ever so slightly 4s. 4s is lower in energy than 3d. That's why 4s is before 3d in the fill order. And after 3d comes 4p, and then 5s, and then 4d, and then 5p, and so on. So notice how it shows the different number of circles. Those different circles represent the number of orbitals. Okay, so this would be a good time to pause and work on the first couple of problems on the worksheet that ask you to write the SPDF notation for elements. And the next section is going to be on how to write shorthand. Okay, so shorthand method is a quick way of writing an SPDF notation with less writing. Kind of like how scientific notation, shortens a number, possibly depending on how many zeros there are in a number. So, for example, for the element like argon, right? I'm sorry, for this element here, right, potassium. If I said, let's write the SPDF notation for potassium. Potassium has 19 electrons. And so 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. If you add these up, these are 19 electrons. Well, as you can imagine, these get really long, especially if you're talking about the elements that are very heavy and towards the bottom of the periodic table. So rather than write all of those, there's a shorthand method. So the way that you do the shorthand method is locate the element whose configuration you're writing on the periodic table. Okay? In this case, we're talking about potassium right now. So you find potassium, you see potassium is element number 19. Follow the row of elements to the far right and then move up one row. If you went all the way to the far right from potassium and moved up, then you would end up with argon. So essentially, here's K. Right, and so if you went to the far right and then you moved up 1, that would bring you to argon. So it says write the element symbol in brackets. Argon. And then add the additional electrons needed following the order of fill. So argon represents the first 18 electrons. So this whole bit right here represents argon. And look what's left after you establish argon in brackets. You only have the 1 electron left, which is in 4s1. So that's why we write argon and 4s1. And that's what we call shorthand. So you can do this with any element. Shorthand method, because of the way we do it, it will start with a noble gas. And a noble gas is this entire column right here. Right here, the very, very last column. Those guys are called noble gases. So the shorthand method is always going to start with one of those. And in total, it's still going to be a correct count of electrons because argon counts for 18 electrons. So instead of writing the Spdf notation, which counts for the first 18 electrons, you're just using argon, kind of like a bookmark, all right, since it's equal to it. Okay, so another example. Let's pick a new element like cadmium. So take cadmium and let's write our shorthand method. Cadmium is element 48. There's 48 electrons. Now, if I find cadmium on the periodic table, you know what? Let's see if I can find the picture again. Okay, so cadmium is right here. All right, where the red circle is. That's cadmium. So if we move all the way to the right, and then you move up 1, that puts you in this box right here. Can you guys find the element that's in that box? That is krypton. And krypton's atomic number is 36. So we write krypton in brackets, and we understand that krypton represents 36 electrons. So what follows krypton on the periodic table to continue writing this out here? Well, krypton, if we go back and look closely at this, notice how krypton completes the 4p sublevel, right? Everyone see how this whole sublevel here is 4p? And krypton is the last one in the 4p. So really, if krypton is the last one in 4p, what comes next after 4p? If we look at our diagram, sorry, all the scrolling, what comes after 4p? Well, it's 5s. So I'm going to write 4p6 because krypton really means the 4p6 block. And then we write 5s. Okay, so put a 2 there. That's 36 plus 2 is now 38. What comes after 5s according to the fill diagram? 5s is followed by 4d. So I write 4d. And if I write a 10 here, this now brings my number of electrons from 36. I'm going to add these up. So 36 plus 2 is 38. Plus 10 is 48, which matches. And this is the shorthand for cadmium. And so there's a lot of backtracking and a lot of checking orders when you do it this way. It saves you writing, but at the beginning, it's going to take you a little bit longer to figure out what you should be beginning your shorthand notation with, like when you're trying to figure out what to write here after the noble gas. So it's going to take practice, and you'll have plenty of practice here on the homework. Okay, and I know this is getting a little long here. The last topic to talk about for this lesson is what we call orbital diagrams. And again, I know that the information here in these notes are pretty dense, so this might merit a stop and rewatch, or at least watch it in sections. And of course, we'll go over it again in class when I see you next. Okay, so remember that diagram that had all those circles that represented the orbitals here? Right, so this is fill order, and you're seeing orbitals here. And so hopefully you understand why there's one circle or one orbital for S, how there's 3 circles for P, how there's 5 circles for D, and 7 circles for F. Right? We talked about how like each of these new sublevels gets more complicated and bigger. So orbital diagrams is another way of showing the organization of the electrons in an atom, but it does so, and it gives us a little bit more information, and it follows mostly the same rules. All right, so nitrogen, for example, 7 electrons. We write the Spdf notation as 1s2, 2s2, 2p3. Okay. So an orbital diagram is just a picture with a bunch of circles showing where the electrons are. So when we filled this, and I'm going to redo it here so you can see the thought process. 1s2, 2s2, 2p3. Okay, so from left to right, or always from left to right, start with the lowest energy. The first electron that goes in an orbital faces up. The second electron that goes in an orbital faces down. And we have to fill one orbital before we start another. We have to fill a sublevel. So we have to fill 1s before we begin 2s. So in the orbital of 2s, first electron faces up, second electron faces down. Okay, that's 4 electrons so far. We have to show 7. So now in 2p, when we have more than one orbital in a sublevel, we put 1 in each before they can be paired. All right, and this is known as Huns Rule. All right, so which essentially translates to do not pair electrons unless you have to. So since I've got 3 electrons, I would write them as the first one goes in there, the second one goes in there, and the third one goes in there. And that's the correct way to show the electrons in this orbital. Here's an example that would be wrong. One, 2, 3. Okay, that would be incorrect, because the reason why we have to put them in one at a time is because that's what's going to be the lowest energy, and lowest energy means most stable. Lowest energy. If you spread them out 1, 1. The reason for that is 2 electrons right here in the same orbital, when there's one open orbital here, doesn't make sense. What happens to 2 things that have the same charge and you put them next to each other? They repel. So this second electron that we placed in here, it actually wouldn't even stay there. It would get pushed and would end up here in this open orbital. Okay, so electrons naturally spread themselves out, and that's what's going to end up being, there's going to be the fewer repulsions that way, and that's going to be more stable. And that's Huns Rule. Electrons must spread out. Okay, they cannot be paired unless they have to be paired. So what do I mean by have to be paired? Well, this next example, oxygen, which has 8 electrons. So 1s2, 2s2, 2p4. All right, so first sublevel, 1s. There's the first, there's the second. Second orbital, 2s. Here's the first, here's the second. Okay, it's 2p. We have 4 electrons. 1, 2, 3. And I still have to place one more electron. So since I have one more that has to be placed, now I go back and I put it in the leftmost orbital of that sublevel. It has to be paired, so I got to put it somewhere. So I'm just going to come back and place it in the first one. So yeah, it's paired, but there's no other open orbital, so that's where it's just going to have to be. Okay, so let's try a couple. Sodium, 11 electrons. So sodium is 1s2, 2s2, 2p6. Notice I'm spacing them out because I'm anticipating having to draw orbitals here. 3s2, 3p6. Oh, actually, we don't actually need that much. Scratch that. Okay, 11 electrons. 1, 2. Second sublevel. 3, 4. Now we're in 2p. 5, 6, 7, 8, 9, 10. And 3s has 1 electron. That's the orbital diagram for sodium. Go ahead and pause the video and see if you can do the orbital diagram for chlorine. Okay, so let's see what chlorine would look like. Chlorine has 17 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6. Okay, first orbital, 1 up, 1 down. Second sublevel, 1 up, 1 down. Third sublevel with 3 orbitals, up, 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 down, down, down. Okay, that is 10 so far. Next sublevel, 3s, up, down. That is 12 so far. I have to get to 17. Up, 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 down, down, and that's 17. And I'm done. That's the orbital diagram for chlorine. Okay. You can go ahead and try the other ones, the vanadium, carbon, and neon. Shorthand orbital diagrams are done the same manner. So let's say I wanted shorthand for chlorine. Okay, so if that were the case, I know that chlorine, if I go all the way to the right side and go up 1, that's neon. And neon represents 10 electrons, and it's the 2p6 position. So really, since I need to get to 17 electrons, I got to ask myself, all right, well, what comes after 2p? Well, it's 3s. And then what comes after 3s? It's 3p. And there's only 5. So we can write shorthand for orbital diagrams the same way we figured out shorthand for the notation. Okay, so you might be thinking, okay, that's great. So we draw a bunch of circles with electron configuration. What is the point? Why do we even do this in the first place? Well, orbitals give us a lot of information. And aside from information that's going to be really useful when we talk about bonding in the next unit, we can tell whether elements are going to be magnetic or not. So when we have unpaired electrons, they cause an imbalance within the electrons in the atom. They're imbalanced. and we call that paramagnetic. Paramagnetic means it will be affected by a magnet. So like this, going back to chlorine that we just drew here, you see that unpaired electron? That would cause chlorine to be very, very, very minimally, but have some paramagnetic characteristics. If we look back, sodium has one unpaired, also very, very, very slight. One unpaired doesn't do a whole lot, but here, when we look at oxygen, we've got two unpaired electrons, so this would be more paramagnetic than sodium would, because the more unpaired electrons there are, the more magnetic it's going to be. And some elements have just, or only have paired electrons. And if they only have paired electrons, the term for that is diamagnetic. Notice how the beginning the prefix is different, which is unaffected. Unaffected. So that would be something like neon, right? So neon is 1s2, 2s2, 2p6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are a little off center there. Let me fix that. So everything here is paired. All are paired. No unpaired equals diamagnetic, and it's not affected by a magnet. It has no magnetic field. Okay, and that's pretty much everything. Your homework is the homework on Spdf notation and electron configurations, which is homework 2.